Welcome back to your initiation into the dark art of linear algebra. We are moving into chapter 5 now, where you will learn about the determinant of a square matrix. In this video, we will discuss the determinant's meaning and some of its basic properties, both geometric and algebraic. The determinant is usually introduced algebraically in most treatments, but I find it is much easier to understand if it is introduced geometrically, which is what I will do here, and of course what I do in the book. So let's get to work. As I mentioned a moment ago, the determinant is something that is defined only for square matrices. We'll see why this is so in a moment. And square matrices correspond to linear maps from a space to itself, say from R2 to R2, or from R3 to R3. And of course, you know from the earlier chapters that linear transformations, or the matrices that represent them, act by transforming the standard basis vectors, that is, by moving them to new locations, which then drag everything else in the input space in their wakes, because the standard basis vectors determine simple and clean grids of squares, cubes, or hypercubes in higher dimensional spaces, and the matrices, the linear maps, act as grid transformations, rotating and stretching everything in space into new forms. Now, if A represents any old square matrix, then the determinant of A, which we write this way, det of A, is a number that tells us two things. First, the magnitude of the determinant of A, in other words, its absolute value, is what I'm calling the volume magnification factor of the underlying linear map. Now, you probably have a sense of what I mean by that when you look at this picture down here, but let's dwell on it a little more, especially on this word volume. I put volume in scare quotes here because it is supposed to cover not only ordinary three-dimensional volume, which is the kind of thing we might think about for a 3x3 matrix, but also ordinary two-dimensional area, which is, of course, what we would think about in a 2x2 matrix. And also in higher dimensional spaces like R4, but it could be R5 million if you like, a square matrix still determines some kind of grid transformation. I just can't draw it very well, but its standard basis vectors, which generate some sort of unit hypercube, and then we would have these unit hypercubes filling all of 4-dimensional space or 5-dimensional space or whatever, just like we had ordinary cubes filling 3-dimensional space. The linear map transforms those basis vectors, and the original nice grid, though here of unit hypercubes, gets transformed into a rotated and stretched grid of what? Well, in this case, the squares became parallelograms, the cubes became parallelepipeds, and in higher dimensional space, the hypercubes become what are called parallelotopes. Be that as it may, provided there is no dimension crushing, so as long as this map is invertible, or however you want to say that, as long as its kernel consists only of the origin, but however you say it, if no dimensions are crushed, then the transformed basis vectors determine a grid of these parallelotopes that pervade all of the higher dimensional space. So again, provided that no dimensions are crushed, we have areas becoming areas in the two-dimensional case, volumes becoming volumes in the three-dimensional case, and hypervolumes of whatever dimension becoming hypervolumes of the same dimension in higher dimensional cases. Now all this brings us back to this definition of the determinant that we are building up. It's a number that tells us two things, one by virtue of its magnitude and the other by virtue of its sign, whether it's positive or negative, but I'm holding off on that one for a moment. Let's concentrate on the magnitude first. I said that the magnitude is the volume magnification factor of the underlying linear map, where volume in scare quotes is standing in for area in the two-dimensional case, volume in the three-dimensional case, and whatever sorts of hypervolume in the 4 and higher dimensional cases. Of course, when we distort a space of whatever number of dimensions with a linear map, the effect is the same throughout the space. I would just continue this grid of parallelepipeds, for example, all throughout R3. It's not like in some other region it would start looking different. It is just a straight transformation of the grid. That's the hallmark of a linear map. A nonlinear map might do all sorts of crazy things to a space, but that's not what we're dealing with here. The hallmark of linearity, after all, is that once we know what it does to the standard standard basis vectors, we know what it does to everything because the grid just gets transformed throughout the entire space in the exact same way. So as we stretch and twist our standard basis vectors, volumes, in this extended sense, get changed in the spaces. They get magnified. And here too, maybe magnification should be in scare quotes as well, because magnifying seems like it should imply it makes them bigger, which is how I drew them in this case. But we could, of course, have a linear map where the volumes get smaller. But anyway, I think you see the point. And so the idea is, look at these unit cubes, hypercubes, or squares. Start in the two-dimensional case. These are unit squares, 1 by 1. So of course, as the name suggests, each square has an area of 1 square unit. But of course, after the mapping in the image, that area, that volume in the extended sense, gets magnified. And let's just say for the sake of argument that now each of these parallelograms has area 2.3 square units. Well, if that were so, that would tell us something about the determinant of A, or at least about its absolute value, its magnitude. It would tell us that that determinant's magnitude must be 2.3, because this linear map, which is represented by the square matrix A, is scaling volumes, areas in this case, by a factor of 2.3. And note that if it's scaling these unit squares by factors of 2.3, it's scaling everything in the plane by 2.3. I explain this in detail in the book, and I'll leave it to you to look into that. Anyway, similar story down here with matrix B. We have our standard basis vectors, which of course generate unit cubes, each of which has a volume of 1 cubic unit. And let's say that the images of those cubes are these parallelepipeds, and let's say their volumes are each 5 cubic units. In that case, we would know that B's determinant is, at least in absolute value, 5. So the determinant itself must either be 5 or negative 5. To make that distinction, we'll need to know what the sign of the determinant signifies, and we'll talk about that soon. But I guess while I'm at it, and I've got this last picture here, I should say that our unit hypercubes, whatever they may look like to four-dimensional eyes, well, they're 1 by 1 by 1 by 1. All the dimensions are perpendicular to one another, so the volume, the four-dimensional hypervolume in this case, would be 1, not cubic unit, but I guess we would say quartic unit. And when we transform four-dimensional space with the linear map that the matrix represents, those unit hypercubes would get transformed into some sort of four-dimensional parallelotope. And let's just say for the sake of argument that it turns out in this case that each one of those guys has a hypervolume of 2/3 of a quartic unit. If that is so, then the determinant of C in absolute value, all we know is its magnitude, would be 2/3. Again, the determinant itself might be 2/3 or it might be negative 2/3. That all depends on this second condition here, which governs the sign of the determinant. So we had better talk about that now. Okay, to explain what the sign of the determinant tells us, I figured it would be easier if I had some dynamic pictures to work with. So I have jumped onto GeoGebra and a graph that we used in an earlier video, which will serve us well once again. And I used this when I first talked about linear transformations and the idea of a grid transformation, in that moving a basis vector around, one of the standard basis vectors around, we end up transforming the entire grid. And when I initially did this, back in chapter 3, you might have wondered if there was any significance to the winking face and the letter R. And actually, there is some significance. I used these two figures because they both have clear orientation, in the sense that they would look different if they were reflected in a mirror. In particular, the winking face has his right eye open, but if you were to hold that image up to a mirror, you would see a face with its left eye open. Similarly, if you were to put a mirror before the R, then the reflected R through the looking glass would come out backwards. It wouldn't be a character in the English alphabet anymore. It's a character in the Russian alphabet, I believe. Okay, fine, you might be saying, but what's the big deal? Who cares? Well, you'll see who cares if I move these basis vectors around in such a way that one of them crosses through the span of the other. For example, let me take this green basis vector that I'm moving around right now and pass it through the span of the other one. Aha! We are through the looking glass. This linear transformation has reversed the orientation of R2 so that our capital R now shows its mirror image, and the face, which was originally looking at you with its right eye is now looking at you with its left eye. So long as we move the basis vectors in such a way that we don't get one crossing over the span of the other, well, then the orientation, whichever way it started out, stays the same. The orientation changes as soon as one of those vectors crosses through the span of the other one. So you see what's happened. I changed orientation twice, and we are back to the original orientation. We have our capital R, maybe it's upside down, but we recognize it's still an R. It's not that weird Russian character. And the face, once again, is looking at us through its right eye. So when we are thinking about any linear map on R2, we can always ask the question, does it preserve orientation, as this one does, or does it reverse orientation, as this one does? Determinant is defined so that if the map preserves orientation, then the determinant is positive. If it reverses orientation, the determinant is negative. That's the idea. Now, we have to be able to think about this, however, in spaces beyond R2. For example, let us consider what happens in R3. Here I have the standard basis vectors, which form a unit cube, and I've got this fella standing on top with a very long nose, flippers for feet, wondering what he is doing, and he is scratching his head with his left hand. Well, if we transform R3 by hitting it with a 3x3 matrix, of course the grid of cubes, only one of which I've drawn here, will get transformed as a result, but so long as none of the vectors, none of the standard basis vectors I mean, cross the span of the remaining vectors, then the orientation will be preserved. However, if we take one of the vectors, like I'll take k hat, which is pointing straight up, and pass it through the span of the other two, so through the plane determined by the other two vectors. If I do that, then what happens to our little man? He's currently scratching his head with his left hand, but if we let this vector pass through the span of the other two, then he goes through the looking glass, and lo and behold, he is scratching his head with his right hand. We have reversed the orientation. If he has an old-fashioned pocket watch and pulled it out, he would find that it now runs counterclockwise. If he has a mole on his right cheek, he will find that it is now on his left cheek, and so on and so forth. Let's restore him to his original orientation. Once again, he is scratching his head with his left hand. Now, there was nothing special about this basis vector passing through the span of the other two. If, for example, I were to take this standard basis vector, this different one, so long as it remains in such a position that it doesn't pass through the span of the other two, in other words, the plane in which the back face of this parallelepiped lies, as long as it doesn't pass through that, then the orientation is preserved. The man remains scratching his head with his left hand. But if I shoot it across that plane, oh, lo and behold, he's scratching his head with his right hand again. We have reversed the orientation. Ay caramba! How do we restore the orientation? Well, of course, we just take one of the basis vectors and pass it through the span of the other two again. And there he is, scratching his head with his left hand again, which was the way he started out. 2 orientation reversals restores the original orientation. Now, I would love to show you a picture of this happening in R4 or R17, but for obvious reasons, I can't do that. Still, the same thing happens. You've got a bunch of standard basis vectors in that space. A linear map moves them around. Every time one of them passes through the span of the others, you get an orientation reversal. The sign of the determinant is what measures at the end of the day whether orientation has been preserved or reversed. So let's go back to the main screen. And here we are again. We were defining the determinant of a matrix. The sign the determinant is positive if the matrix preserves orientation and negative if it reverses orientation. So if we go back up to our initial example in R2, here we had a linear map represented by matrix A that takes the standard basis vectors over to these vectors. Well, it's clear that neither vector crosses over the span of the other as they go from here to here, which means that the determinant would be positive in this case. We already assumed that the volume magnification, or area magnification in this case, was by 2.3, which told us that the absolute value of the determinant was 2.3, but we didn't know the sign. Well, now, since we know that it preserves orientation, we know that the determinant really is positive 2.3. I can remove those absolute value signs. Let's see, how about this one? I wonder if we can tell just by looking at it. Yeah, actually it looks like this one preserves orientation as well. You have to use your spatial imagination here a little bit to see it. If you are familiar with the so-called right-hand rule that has to do with a cross product, which maybe you met either in physics or vector calculus or something, you might also note that you can see you get the same effect in both cases. If you put your right hand so that your fingers are pointing along the yellow vector here, and then you curl them towards the green vector, well, the orange vector is pointing in the general direction of your thumb. And the exact same thing would happen here in the image, which is good, which means that your right hand over here would get mapped to a rotated and stretched version of still a right hand over here. Orientation is preserved. So that means the determinant of B is positive, the determinant of B is 5. Obviously, in this last case, in R4, there's no way to see what's going on. But let's imagine for a moment that to get from here to here, we end up reversing orientation. If that were so, and again, it's hopeless to see in a picture because this is just a purely schematic picture. If that is so, then the determinant of C would be not 2/3, but minus 2/3. All right, you'll find more concrete examples in the book and its exercises, but we've said enough for now about the meaning of the determinant. It gives us a sense of how space is being scaled, how volumes in that space are changing under the effect of a linear transformation. But now we need to turn to some properties of the determinant. One important property concerns the determinant of a product, and it turns out that the determinant of a product is the product of the two determinants, and we want to understand why this is so. Now, in the usual algebraic treatment of determinants, you don't define a determinant this way. You define it through a very complicated formula that takes the entries of a matrix and produces some number out of it. We will see that formula at the end of chapter 5, by the way. And then you have to prove that this crazy-looking formula has, as a consequence, this property. And ultimately, if you are lucky, you will prove that what that formula is computing is all this stuff. But sometimes that hardly gets mentioned at all. I think it's much preferable to turn everything on its head, start with the real geometric meaning of the determinant, use it to derive basic properties in very natural ways, and then at the end of the day, use those properties to figure out a way to actually compute the determinant, to come up with a crazy formula. And we'll do that in good time. But for now, let's use our geometric meaning to understand why this is true. It's almost obvious if you understand what matrix multiplication corresponds to geometrically. As you learned back in chapter 3, matrix multiplication corresponds to function composition, the composition of the linear maps that these matrices represent. But just think of an example, and this will be almost obvious. Let's suppose that A and B are two square matrices of the same size, maybe 3 by 3 matrices, and that matrix B scales volumes by a factor of 3 and reverses orientation. Who knows what it does precisely, but let's just suppose these are the two things that are involved in the determinant. And then let's suppose matrix A scales volumes by a factor of 6, and it also reverses orientation. Now we have enough information here to write down the determinants of the individual matrices. The determinant of B is -3, and the determinant of A is -6. But the question is, what can we say about the determinant of the product AB, which is a new matrix? Think about this geometrically. It's very clear, because the product of those two matrices represents the composition of those two linear maps, reading right to left. So the effect of this product on the space it's acting on is simply the effect of hitting that space first with B and then with A. But what happens if you do that? You hit the space with B, all the volumes get scaled by a factor of 3, and the orientation gets flipped. You take that result, feed it into A, and what happens? All the volumes get scaled by an additional factor of 6, and the orientation flips again. So of course, the overall effect is that the product matrix scales volumes by a factor of 3 times 6, or 18, because that's what happens when first you triple something and then you sextuple it. You end up multiplying it by a factor of 18, 3 times 6. And how about the orientation business? The product matrix preserves orientation, because First, if you flip it and then you flip it again, well, you flipped it back to where it originally started, hence the preservation of orientation. Put all that together and it tells you that the determinant of AB is going to be positive 18, which of course is the product of the individual determinants. -6 times -3 is 18. And I hope it's clear to you that this would happen under all circumstances. It should be obvious. Multiply the two scaling factors, and as for orientation reversals, well, now you see why we connected them to the sign, because they work the same way that factors of -1 do. If you put two factors of -1 together, you get a +1. Well, you put two orientation reversals together and you get orientation preservation. If we had a product of 7 different matrices, 4 of which reversed orientation and 3 preserved it, you would have 4 factors of -1 and 3 of 1. Put it all together and you get 1. Which would give you preservation, or a positive determinant. Okay, anyway, you can meditate on that more on your own. I hope this gives you the basic idea. Let's look at another important algebraic property, which is that the determinant of an inverse matrix, determinant of A inverse, is the reciprocal of the determinant of A. Why does this one happen? Again, it's totally obvious. If you remember what A inverse does, it undoes whatever A does. So if we have some square matrix A that scales volumes by a factor of 22 and it preserves orientation, well, then if A inverse is going to undo that map, obviously it must scale volumes by a factor of 1/22 to bring the things that had been scaled up by a factor of 22 back down to where they were originally. And since the original map preserved orientation, well, the inverse will still preserve it so that their product preserves it. So in this case, the determinant of A would be 22 and the determinant of A inverse would be 1/22. Now, if it hadn't preserved orientation, if instead it reversed orientation, then of course the determinant of A would be -22, but then in that case, A inverse wouldn't preserve orientation either. A inverse tries to take whatever A did and get it back to its original state. So if A reversed orientation, A inverse has to flip it back. So A inverse would have to reverse orientation too, which means that the determinant of A inverse would have to be -1/22. And we still have that the determinant of the inverse is the reciprocal of the determinant. And again, a little meditation on this fact should show you that this always happens. By the way, there's another way to see why this is true that combines some simple algebra with the kind of geometry we were talking about. Very quickly, we know the product A inverse A is of course the identity matrix. Well, let's take the determinants of each side. What's the determinant of the identity matrix? Well, the identity matrix doesn't do anything. It doesn't scale volumes, or it scales them by a factor of 1 in the trivial sense, and it preserves orientation. So the determinant of the identity matrix is of course 1. Yeah, but what about this stuff, you might say? Oh, that's easy. It's easy because we just proved this property about the determinant of a product, which is what we have right here. The determinant of that product is the product of those determinants. Well, now all we have to do is just solve for this. In other words, divide both sides of this equation by the determinant of A. And when we do that, we get that the determinant of A inverse is 1 over the determinant of A as claimed. So again, another nice interaction between geometry and algebra. Be sure you understand both of the arguments that led us to this result. One purely geometric and one making use of this first property that we proved. So they give you slightly different insights. Good. There are 2 more simple properties I want to establish. The first of which will link determinants to invertibility. Namely, a square matrix A is invertible if and only if its determinant is not 0. This equivalence, again, is more or less obvious if you understand what's going on geometrically. To get a feel for it, let's just think about the case of a 3x3 matrix. Such a matrix, of course, maps R3 to R3, and if it is invertible, then of course it doesn't collapse any dimensions, which means that the 3 standard basis vectors get mapped in such a manner that they are linearly independent and therefore generate some sort of parallelepiped, which occupies, of course, 3 dimensions, and the entirety of the space is filled with those parallelepipeds. But the important thing here is that it has some non-zero volume, which means that the determinant of this invertible map must indeed be non-zero. If, on the other hand, matrix A is not invertible, then this map could not be one-to-one. We would get lots of points collapsing into individual points in the output space. We would have dimensional collapse, and the only way for that to happen would be for the standard basis vectors to get mapped to a set of linearly dependent vectors, such as these that all lie in a plane. Well, in such a case, what would the determinant of this non-invertible map have to be? Well, think about what the determinant means. Its magnitude is the volume magnification factor of the map. Well, what happens to this unit volume right here when we map it over here? What's the volume of the image of that cube? Well, the image doesn't have any volume because it's squashed into a two-dimensional plane. This lovely cube would become some nasty tangle of line segments within this plane. That stuff cannot have any volume because it is now a two-dimensional object. It requires 3 dimensions to have volume. And I know I said we were thinking of volume in an extended sense over here. That's true, though perhaps I should have been a little more clear. In fact, I am clearer about this in the book. If we wanted to make this a little more precise, we could say if A is, rather than saying a square matrix, an n by n matrix, then the magnitude of the determinant is the n-dimensional volume magnification factor of the underlying linear map. So if we have this non-invertible map like this, from R3 to R3, what the determinant is measuring is the 3-dimensional volume magnification factor. And since it goes from 1 unit here to no units here, we are multiplying by 0. So if A is not invertible, the determinant must be 0, because volume, n-dimensional volume, is all squashed out of existence after the map. So now we know that invertible maps have non-zero determinant, and non-invertible maps have 0 determinant. So if we have a matrix whose determinant is 19, we automatically know that it's invertible because that's a non-zero determinant. If we have a matrix whose determinant is 0, we know that the matrix is not invertible. Okay, one more thing, and unlike these 3, this one is not so obvious. We will have to do some calculations to see why it is true. We still haven't talked about how to actually compute a determinant, and that will be the main theme of the next lecture. But in the special case of a 2x2 matrix, it turns out that there's a simple way to compute it that we can discuss right here. Namely, if we have a 2x2 matrix, then there's a very simple formula in terms of its 4 entries. Namely, we take the product of the 2 entries on the main diagonal, so AD, given the way that I've labeled them here, and then from that product, we subtract the product of the 2 off-diagonal entries, so in this case, BC. And so we have a very simple formula for the determinant of a 2x2 matrix. Why is this so? We know that this 2x2 matrix takes the standard basis vectors and maps them to new locations. Now, I've drawn these new locations in a fairly convenient location. They need not appear in such a convenient location, and if they don't, then you have to make a few little adjustments to the argument that I'm going to make now, and that's something I leave you in the homework problems. All right, so this yellow vector is the image of I hat, so its coordinates are given by the first column, A and B. So for example, if I drop a perpendicular here, I get a right triangle that is A units in this direction and B units high. And while I'm at it, I might as well put the components of the second column, which are the components of the second vector, on as well, C and D. Now we have the individual entries of the matrix in our picture, which is good because we want to express the determinant in terms of those individual entries. But where does the determinant show up in this picture? Well, that, of course, is going to be the area of this parallelogram that is determined by the 2 vectors, which are the columns of the matrix, because we're going from the unit square in the input space, whose area is 1, to this parallelogram in the output space, whose area will be 1 scaled by whatever the determinant is. So therefore, it will be the determinant of A. And the way I have arranged these, as I said, I put them in a fortuitous position. It's clear that the orientation has been preserved. I've never had to pass one vector through the span of the other to move them from this position to this position. We want to express that area, that determinant, in terms of these 4 symbols, A, B, C, and D. With a little thought, we can supplement this figure by drawing in some more lines parallel to the axes like this. Okay, this lends a pleasing symmetry to it, but does it help us? It does, because now we have some more right triangles and some rectangles too, and everybody knows how to find the area of a right triangle or a rectangle. So what we can do is we could start with the area of this big rectangle. Looks like a square in my figure, but it doesn't have to be a square. Get that area in terms of A, B, C, and D, which should be easy, and then just subtract away the other pieces, the rectangles and right triangles, and what we will be left with is the determinant we seek. So let's do that. It's going to help if I write down the side lengths for all of these other triangles and rectangles. This right triangle right here that I've just filled in is congruent to this triangle over here. So they have the same dimensions. So I'll go ahead and fill those in. And similarly, this triangle right down here is congruent to this right triangle up here. So they have the same dimensions, which means that I can fill in those sides too. And while we're at it, opposite sides of rectangles have the same lengths. So this one down here will be C, and similarly this side over here will have to be B. Doing the same thing with this rectangle, we can fill in its sides too. Now, to get back to what we were saying, we can write down an expression for the determinant if we observe that that determinant, that area of the parallelogram, is the area of this large rectangle, which I've just put in orange, minus the areas of these little pieces that surround the parallelogram. Okay, so what's the area of the big orange block? Well, it's A plus C on this side and B plus D on this side. So that's going to be A plus C times B plus D. But now we have to subtract away the stuff surrounding the parallelogram. Well, let's start with the two small rectangles. That's easy. They each have area B times C, so we'll subtract away 2 BCs. Good start, but we still have to get rid of the right triangles. This right triangle and this right triangle are congruent. In fact, you could bring them together so that their two hypotenuses meet. You can imagine sliding this one into that position, and you would just get a rectangle, a C by D rectangle. So subtracting all that area away would take away CD, and then we could do the same thing with the remaining two right triangles. If you bring them together, glue them together at their hypotenuses, you get an A by B rectangle. So we have to subtract its area away as well. And now we have an expression for the determinant. If you give this to your favorite Algebra 1 student, he or she will quickly tell you that that is equal to this stuff. And now we get a lot of cancellation. We have a plus AB and a minus AB. We have a plus CD and a minus CD. And what's left over? Well, we have AD, and then we have a BC, but then we're subtracting away 2 BCs, which leaves us with minus BC. And that is indeed what we were aiming at. And we have established our formula for a 2x2 determinant. And as I said before, in the homework, you'll do some problems to show that this formula still holds, even if the vectors don't get mapped to such nice positions. Good. So this is a formula everyone should know. And if nothing else, it quickly allows us to rewrite the formula we came up with, or you came up with in an exercise, for the inverse of a 2x2 matrix. You showed in an exercise in the previous chapter that if I have a 2x2 matrix and I invert it, we get this funny result where the off-diagonal entries end up sprouting negative signs, the two entries on the main diagonal end up switching places, and then we had to divide through by this funny expression, AD minus BC, which we get by zigzagging through the matrix like that. And now we can recognize, oh, I know what that is. That's the determinant of the matrix. So I could just replace that with the determinant of A, and everything looks much neater. To invert a specific 2x2 matrix, like the one I've just written down, you negate the off-diagonal entries, flip the ones on the main diagonal, and divide by the determinant of that matrix, which we can see is 5 minus 8, therefore minus 3 down there. And you could either keep that as is, which is nice because you just have whole numbers, or if you like, just write it in one piece by doing that scalar matrix multiplication. Use whichever form suits the occasion. Okay, that formula for the determinant of a 2x2 matrix in terms of its entries gives us some impetus to seek a general formula for computing the determinant of any n by n matrix. We will come up with a way to do that, as I've said in the next video, but what I want to do in the remainder of this video is pave the way towards that result by coming up with the determinants of two very special types of matrices. The first is a shear matrix. Now, a shear is a particular kind of linear transformation that is best explained through some examples, especially if we build up dimension by dimension. So let's start in the two-dimensional case. If we transform R2 with a shear parallel to the x-axis, that will work as follows. The standard basis vector lying along the x-axis is frozen. It doesn't move at all, but the remaining standard basis vector will move. It will move in such a way that its tip moves parallel to the x-axis. So it will have to end up somewhere on this horizontal line, the line y equals 1. To pick something definite, I'll go ahead and put it here so that the image of j hat looks like this, and the actual shear matrix would be, let's see, well, I hat gets fixed, so that's still 1, 0, and j hat moves in such a way that its second coordinate remains 1. So this has to be 1, and the remaining entry, well, I'll just put it at 1/2, but if that had been any other real number, we would have had just a different shear. And you should be able to see what the overall effect on the plane would be. We would be going from the standard graph paper grid to something like this. So the effect is to take every individual square in the original grid and simply push it over a little bit so that it comes out slanted. As we go from these squares to these parallelograms, the heights do not change. That's why it was so important that we ended up on this line, or equivalently, that this entry in the matrix ended up being a 1. And the lengths of the bases of the boxes don't change either. They get moved over a little bit, like this one right here, of course, does get moved over, but it's going to have the exact same length that it had in the original case. And it's easy to see why. The length of that side of that parallelogram is, of course, equal to the length of this side of the parallelogram. And that side is just the original length of the base. And I think a nice image to have in your head for a shear is to imagine taking this square, the one determined by the standard basis vectors, and thinking of it as a collection of very thin rectangles stacked on top of one another. Now, I've only drawn about 15 of them here, but you have to imagine thinking about this the way you would, say, in an integral calculus class, where it consists of infinitely many, infinitesimally thin rectangles. If we think of it that way, then we can think of what the shear is doing is just pushing each rectangle in the stack to the right. It doesn't push the bottom one at all, and the higher up we go, the more it pushes it, so that we end up pushing our stack a little bit, the way we might push a deck of cards into a new position, like this. And that pushing, I think, gives a nice sense of what a shear does. Moreover, it helps us see a very important result. It's going to help us understand the determinants of shear matrices. So let's think about this particular one we're looking at here. Now, on one hand, you might say, oh, it's a 2 by 2 matrix. I know how to compute the determinant of that. I just established a formula for it, right? It's 1 minus 0, so the determinant is 1. Wasn't that easy? A little too easy. We want to think of the determinant here geometrically, because doing so will help us understand not just 2 by 2 shear matrices, but 3 by 3, 4 by 4, and so on and so forth. We'll be able to generalize our geometrical understanding, whereas we only have a formula at this point for our 2 by 2 case. So anyway, what's another way to see that the determinant of this shear matrix is 1? Well, there are several geometric ways we could see it, but the vital one here is to go back to thinking of the square and the parallelogram as consisting of infinitely many infinitesimally thin rectangles. Because of the action of this shear, each individual rectangle, like the top one in our original square, just gets pushed over and becomes the exact same thing. It's just being translated. On a rectangle by rectangle basis, we're just moving things around. We aren't actually changing the area. Just like, again, if you take a stack of cards and push it with your finger so that the top ones move more than the bottom ones do, you're not changing the volume of the stack. Well, if you're not changing the volume, or in this case specifically you're not changing the area, what do we know about the determinant? Well, the determinant has to be 1 because of the basic meaning of the determinant. It's the factor by which we multiply areas. Well, the area is not changing at all, so we're just multiplying by 1. And obviously, we are not changing the orientation, so the determinant has to be positive 1. And this, in fact, will be true of every shear matrix, whether we're shearing parallel to the x-axis or parallel to the y-axis, or whether we are doing a shear in 3D of various sorts, or 4D or 5D or whatever. It's easy to understand it in this case, and if you can understand it in this case, you should be able to understand it in the other ones as well. And you might say, hey, but maybe there was something special about the fact that you put this at 1/2. Not at all. If instead, for our shear parallel to the x-axis, we had mapped j hat to, say, the vector -2, 1, so its tip is still on that line. And now the matrix would have, instead of a half, it would have a -2 there. The determinant would still be 1. And again, we can see this by our formula very easily. 1 minus 0 is still 1, but we can see it geometrically too. I'll need to move this over a little bit, but the only difference in our picture here would be that our squares here get mapped to much more severely skewed parallelograms, which on our picture down here would translate into something more like this. Each of the original infinitesimally thin rectangles just gets mapped to a new infinitesimally thin rectangle with the exact same length. The length doesn't change. All the cross sections remain the same. So we haven't actually changed the area, and consequently, the determinant of the matrix must be 1. Good. And just as we can shear parallel to the x-axis, we can shear parallel to the y-axis. Now that is the one that stays fixed, while the other standard basis vector moves in such a way that its tip has to slide along x equals 1. So let's just say, for the sake of argument, that it ends up here at the point 1, 1. The grid of squares becomes a grid of parallelograms, of course. And what about the matrix corresponding to the map? Well, the second column stays fixed, so it's going to be 0, 1, whereas the first one, its first entry, has to remain 1. The other one, though, can be whatever we want. Like here, it looks like it's 1. And so we have another shear matrix. What's its determinant? We can see that with our 2x2 formula, 1 minus 0 is 1, but we understand it geometrically as well. We're taking our original squares, thinking of them as consisting of infinitely many, infinitesimally thin rectangles, here stacked up like books on a shelf, and then we just push some of them up so that they end up like this. We haven't actually changed any area. Area doesn't change. Orientation is preserved, so of course determinant is 1. And before we move on to the 3x3 case of shear matrices, think about the general picture. Don't be distracted by the -2 here and the 1 here. If this -2 in the upper right corner in our shear parallel to the axis had been anything, so let me just replace it with an asterisk, we should recognize that this is still a shear matrix. It fixes I hat, and j hat gets mapped to something 1. So it will end up with its point on that line, and we end up with a shear as a result. Similarly, down here, if we were just thinking of a general shear parallel to the y-axis, well, that means j hat has to be fixed, so the second column has to be 0, 1. But the image of I hat, well, all that's important is that its first component is 1, because it has to lie on this line. The second component could be anything we like, so I'll just put an asterisk there. Whether its place is taken by a 1 or a 6 or a -9, it doesn't matter. That would give us a shear matrix. And so now we see how to get a shear matrix parallel to one of the axes for a transformation of R2. We start with the identity matrix, but then we pick either column of it, and we can change the 0 in that column to anything we like. And if we do that, we get a shear matrix. Okay, we'll be seeing something like that again when we turn, as we will now, to shears in R3. Now, when we carry out a shear in R3, we're going to shear parallel to what? Not one of the coordinate axes now, but one of the coordinate planes. In other words, the xy plane or the yz plane or the xz plane. Let's do a shear parallel to the xy plane. Well, the way this works is that the standard basis vectors that lie in that plane, they remain fixed. When we're doing a shear, only one standard basis vector is going to get moved. So in this case, it'll be the one along the z-axis. That's the only one that's not frozen. But it's still constrained. It can't change its third coordinate. We can move the tip of that vector not to any old point, but we have to move that tip so that in the motion it remains parallel to the xy plane. In other words, it's going to be constrained to the plane z equals 1. Let's say that its tip is at the point 3/4, 1/2, 1. Well, then in that case, our original grid of cubes is going to get mapped into a grid of parallel epipeds. And what can we say about this matrix and its determinant? It's a 3x3 matrix, of course. I hat and j hat are fixed. They don't move. So we know exactly what the first two columns are going to be. As for k hat, we moved it so that its tip was at this point. So that third column is going to be 3/4, 1/2, and 1. That's our shear matrix. Maybe I'll call it S. Well, what do we know about the determinant of S? Hey, we know a formula for 2x2 determinants, but not for 3x3 determinants. So what are we supposed to do? We can get the determinants of shear matrices by thinking geometrically. And the same kind of argument we made over with that picture will work in the three-dimensional case, because I can think of my cube as being composed of infinitely many, infinitesimally thin little slabs with these square cross sections. Each slab looks something like this. It's just a square with a little infinitesimal thickness added to it, like an infinitesimally thin pizza box. Anyway, to carry out the shear, it's like we have a stack of those pizza boxes, and once again, we're just tipping them over. We're pushing them away from the z-axis towards this vector in some sense. But as we do so, we're not changing the volume. Each individual infinitesimal pizza box, it's just changed its position, and the stack has become more precarious. But the volume of the collection of boxes hasn't changed. Since we haven't altered the volume with the shear, there's no volume multiplication factor. And that means that the determinant of the shear is still 1, just as I said it would be. Good. Now, let's make a few observations here. First, there was nothing special about the point 3/4, 1/2, 1. The 3/4 and the half could have been anything. All that mattered was that we kept the z-coordinate 1. So in our matrix here, instead of having the 3/4 and the half, let me just replace those by asterisks to indicate that they could be anything you like, and we would still get a shear matrix, and the determinant would still be 1. So any shear parallel to the xy plane in R3 is going to have this form. The only thing that could differ are those two entries, and whatever you put in there, it'll change the map, but it will not change the determinant, which will be 1, because these shears preserve volume. Now, this was a shear parallel to the xy plane, but there are 3 different coordinate planes we could work with here, and we could shear parallel to any of them. For example, if we shear parallel to the yz plane, the 2 standard basis vectors that lie in the yz plane remain fixed, whereas the one that does not lie in that plane, namely I hat, that gets moved, but it's moved in such a way that its tip ends up in the plane x equals 1. So maybe over here somewhere. What are the coordinates at that point? Well, the first one has to be 1. The other 2, they could be anything. But we end up with a new grid of parallel epipeds. The matrix representation is going to have the second and third columns are the standard basis vectors because they're frozen, and the first column must be a 1 in the first slot, and then it could be anything in the other 2. And yes, once again, the determinant will be 1, because when we're doing a shear, we're just moving some infinitesimally thin slabs, although in this case, instead of thinking of them like this, stacked up like that, we would have them stacked up like this, and then they would get sheared into new positions. You get the idea. Now look at these 2 matrices. We've got the one with a shear parallel to the xy plane here, and the one with a shear parallel to the yz plane here. And without drawing any more pictures, and clearing out a little space, I think you know exactly what's going to happen if we shear parallel to the xz plane. Well, the standard basis vectors in the xz plane will be fixed, and the remaining one, well, the only thing that we have to have happen is that that 1 has to remain where it originally was. What goes in the other slots of that column? Well, anything you like, and you will get a shear matrix. And of course, the determinant of this thing is going to be 1 for reasons we have now been through multiple times. So now, let's just concentrate on these 3 forms of shear matrices parallel to the coordinate planes in R3. What we see is that if we want to cook up a shear matrix in R3 parallel to one of the 3 coordinate planes, there's a very simple recipe. We start with the 3x3 identity matrix, we pick one and only one of the columns, and we can replace the zeros in our chosen column with other numbers. Do that, and you've got a shear matrix. and we know that its determinant will be 1. This is nice because now if we see a matrix like this one, we can recognize, oh, that's a shear matrix, and therefore I know that its determinant is 1 because shearing doesn't change volume. Well, I'll bet you can guess where this is going next. Suppose we have a shear in R4. Now, I really can't draw you a picture, but that's quite all right. You understand what's going to happen. We're going to have a shear parallel to one of the not coordinate axes or coordinate planes, but a coordinate hyperplane. Let's say our shear is parallel to the XYW coordinate hyperplane. Well, that means that the standard basis vectors pointing in the X, Y, and W directions will be fixed. As to the fourth, well, the only thing that's required by the shear is that the third component be 1. The other 3 components can be whatever they want because we're free to move the tip of that third standard basis vector anywhere, so long as it remains in the hyperplane Z equals 1. So this would be a 4x4 shear matrix. And I'll bet you can guess what its determinant is going to be. It's going to be 1 because shears preserve volumes. In this case, we would have a grid of hypercubes, which could be sliced into infinitesimally thin 4-dimensional boxes of a sort. One of those dimensions would be infinitesimal, and we would have infinitely many of them stacked up. And to do the shear, we're just pushing that stack a little bit, so the volume remains preserved, and therefore the determinant is 1. Same story if we were shearing parallel to a different coordinate hyperplane. The only difference is that instead of our matrix looking like the identity matrix, except in the third column we've changed the zeros to other things, we'd be doing that with some other column. Different kind of shear in R4, determinant is 1, which is the important thing for us here. Shears preserve volume. And this same thing happens in R5, R6, R7, R19, whatever you like. If we have a matrix like this one, we can recognize from the shape of the matrix, oh, hey, look, this is the identity matrix, except that in one column, somebody's tampered with it and changed some of the zeros to other things. That means this must be a shear in R7, and consequently, its determinant must be 1. And that is really the thing we want to take away from all this business about shears. We want to recognize when we see one, an identity matrix where one column's been tampered with, the 1 is left alone, but the other entries, the zeros, may have been changed. When we recognize such a thing, we say it's a shear, its determinant is 1. We're going to need this, perhaps surprisingly, when we come up with a way to compute the determinant of any matrix whatsoever. Any square matrix, of course. All right, so let's put our shears down and turn to the last kind of matrix we will consider in this lecture. Let's talk about triangular matrices. A typical example would be something like this, which would be called an upper triangular matrix, as opposed to something like this, which is called a lower triangular matrix. And I think it is fairly obvious where the names come from. And it's perfectly fine for, say, a lower triangular matrix to have a 0 in the lower triangle, or even many zeros, or even all zeros. What makes it a lower triangular matrix is that if there are any non-zero entries, they have to appear in the lower triangle. And of course, the analogous situation holds for upper triangular matrices. Anyway, triangular matrices have some nice properties, one of which concerns their determinants. And this follows from some pretty simple geometry. So let's take a step back and consider parallelograms, parallelepipeds, and their higher dimensional analogs, parallelotopes. And you'll have to forgive me for this appalling representation of a 4-dimensional object on a 2-dimensional screen. Now let's go up dimension by dimension. In the 2-dimensional case, we have a parallelogram, and let's say its base is b and its height is h. In that case, we know that the area of the parallelogram is the base times the height. You know that because it's a well-known formula, but you also know this is true because a parallelogram is just a sheared rectangle. Shears preserve area, and the area of the original rectangle is base times height. So of course, this area is base times height for a parallelogram as well. Good. Now let's move on to the 3-dimensional case. We have a parallelepiped, and what can we say about the volume? Well, a parallelepiped is the result of shearing an ordinary rectangular box. shearing preserves volumes, so the volume of the parallelepiped is computed in the same way we would compute the volume of a box. We get the area of the base, and then we multiply that area by the height. So the volume of the parallelepiped is simply the area of its base times the height. Well, a four-dimensional parallelotope is a sheared version of a four-dimensional rectangular box. Shears preserve hypervolume. So if we want the hypervolume of the parallelotope, it suffices to get the hypervolume of the four-dimensional rectangular box. And like any rectangular object, the way we get that is to start with the base, which in this case would be a three-dimensional base, and multiply by the height, which is that perpendicular distance from the base to the top, just like it was in the three-dimensional case, or even the two-dimensional case. There's just an extra dimension involved. So the hypervolume of our parallelotope would be the volume of its base, which itself would be a parallelepiped, times the height. And of course, this pattern continues up all the dimensions. To get a five-dimensional parallelotope, we'd be taking a four-dimensional one, extruding it out through a fifth spatial dimension, and the resulting five-dimensional hypervolume would be the four-dimensional hypervolume of the base times the height in that fifth dimension. But in all cases, however many dimensions we're working in, we get the volume in the generalized sense by multiplying the base times the height. Once we understand that, it becomes very easy to understand the determinants of triangular matrices. Why is that? Let's look at an example or two and you will see it yourself. Let's think about what the map that this matrix represents does to three-dimensional space. The first standard basis vector gets mapped to 2, 0, 0, which lies along the x-axis. And that will always happen with an upper triangular matrix because in the first column, only the x component can be non-zero. That's going to be important for us in a moment. Now, what happens to j hat, the second standard basis vector? Well, we look at the second column. In this case, it goes to 1, 3, 0. And note that the third component has to be 0 in an upper triangular matrix, which means that for any upper triangular matrix, 3 by 3, we don't know what the first two components are going to be, but the third one is 0, so that means the second basis vector gets mapped to something that lies in the xy plane. So the triangularity forces I hat to get mapped to something just lying along the x-axis. J hat gets mapped to something lying just in the xy plane. And K hat can go anywhere. There are no restrictions on it because there don't have to be any zeros. In our case, it ends up at 3, 4, 5. Now, those standard basis vectors determine a unit cube, whereas their images determine a parallelepiped. And of course, the volume of that parallelepiped is the determinant of T. Well, that's going to be true for any matrix. It doesn't have to necessarily be triangular for that. But the fact that this one is upper triangular makes it very easy for us to see what the volume of this parallelepiped is, because we know that it's going to be the base times the height. But it's easy for us to see what the base of the area is. It's a parallelogram whose base is 2 and whose height, well, that's just the y component of this vector. So the height of that base parallelogram is 3, which means that the area of the base is 2 times 3, in other words, 6. But I'm going to leave it like that, very suggestively. Now that we have the base's area, we just have to multiply by the height of the parallelepiped. And that is, of course, given by the third component of this green vector, the third column in our matrix. And that is, of course, 5. So now we have enough information to write down the determinant of our triangular matrix. It's the volume of this parallelepiped, which is its base times its height. Well, the area of its base, we said, is 2 times 3, and its height is 5. Put that all together, and it spells 30. But the number 30 isn't the important thing here. Look at its factors, 2, 3, and 5. Those are the diagonal entries on the triangular matrix. Those are the only entries that we needed to actually compute the determinant, which was just their product. With a little reflection, you will see why these other entries just didn't come into the picture at all, but I'm going to leave that to you because this has been a very long video. I'll mention only one last thing. In this case, the determinant was positive because clearly the orientation was preserved. You can deform that little frame of basis vectors into this one without having any of them cross over the spans of the others. But of course, that won't necessarily always be the case, and I'll give you a very quick example. This 2 by 2 upper triangular matrix. If we think about what the map does to R2, well, we see the effect on the standard basis vectors, and notice that in this case, the determinant is definitely negative, because to bring j hat to this position, it has to cross through the span of I hat. So if we look at the area of this parallelogram, that will be the negative of the determinant. So if we can find that area and then negate it, we'll get the determinant. But once again, that's easy, thanks to the fact that the first vector just got stretched along the x-axis, which means that the base of the parallelogram is 2. And as for its height, well, that, of course, is just the second component, well, the negative of the second component of this vector. So that's going to be 3. It's a parallelogram. Its area is base times height, so 6, which means that the determinant of this map would be -6 to account for the orientation reversal. But of course, -6 is just 2 times -3. Again, those diagonal entries are the only ones that matter, and multiplying them together gives us the determinant. The negative here takes care of the orientation reversal. Both these examples involve upper triangular matrices. Similar considerations show that it works for lower triangular matrices as well, and again in any number of dimensions. So, quick summary of the result: the determinant of any triangular matrix, upper or lower, whether 2 by 2, 3 by 3, or 100 by 100, is simply the product of its diagonal entries. So that if we see a matrix like this, and we want to know the determinant, it's a piece of cake. We recognize, aha, an upper triangular matrix. The determinant of any such matrix is simply the product of its diagonal entries. So 6 factorial, which is 720. Good. And while this might seem like some kind of mere curiosity, it is not. As you will see in the next video, the way we can compute the determinant of any square matrix will depend directly on this result about determinants of triangular matrices. All right, enough is enough. Goodbye.